let's get started. So we're going to be talking about sequences. And sequences are infinite collections of numbers. And we just put them in a list. So a sequence is an infinite collection of numbers that we make in a list. We can call it A1, A2, A3, and so on. Okay, so it's very much like a finite collection of numbers, except it's infinite. It just keeps going on forever. So let's do some examples. First of all, example 1. We can have this thing, the collection of numbers of the form n over n plus 1. So these brackets here means a set, and we'll put here a little n to indicate that the n is the thing that is moving. So if we have this collection, then let's just see what it is. So A1 is when n equals 1, so we have 1 over 1 plus 1, which is a half, right? A2 is 2 over 3. A3 is 3 over 4, and so on. Yeah? And this is a perfectly well-defined thing, right? So for every integer n, you know what an is, right? Yeah? So this might be an unusual concept for you. If you've seen this at all, you've seen it much less often than a function. But this is a well-defined, meaningful thing, right? This is something that makes sense. Let's do another example. What about this? Minus 1 to the n plus 1 over 3 to the n. Like this. So let's see what this sequence is. So let's take n equals 1. So A1, we're going to have minus 1, 2 over 3. Yeah? So we have minus 2 over 3. Yeah? A2, so we have minus 1 squared, so it's positive. And then we're going to have 3 over 3 to the power 2, which is 9. Yeah? A3, we have a negative sign, minus 1 to the 3 is minus, and then we're going to have 3 plus 1 is 4, so it's minus 4, and then 3 to the power 3, so 3 times 3 is 9, and then times 3 again is 27. It's 27, and then so on, right? So for every n, we know what this an is. It's perfectly well defined. It's a thing, yeah? Yeah. So this is a mathematical object. It is something where we can define, it's meaningful. And it turns out that this is a very useful mathematical object to understand many things going forward. So you've been learning a lot about functions for many years now, right? Which is a mathematical object where for every x along the x-axis, you have some value, right? F of x, yeah? Well, a sequence is a more simple, a more basic mathematical object. For every n, which is an integer, we have a value, an, yeah? And just as a function is very useful for many things, we're going to find out that sequences are very useful as well, yeah? Cool, so that is a sequence. Let's do a simple exercise like this. So sequences don't have to be defined via a formula in this way, but often they are. Here's the kind of example you might see, or kind of question you might see. Find the formula for this sequence. The sequence that goes 3 over 5 minus 4 over 25, 5 over 125, minus 6 over 625, and so on. Okay, so we want to find the formula that is giving this thing, right? So for 1, we have this, for 2, we have this, for 3, we have this, and so on. Yeah? So we look at this and try and determine what structure we have, how we can define these numbers out of n, where n is 1, 2, 3, and so on. So look at it for a second, and then I'm going to ask you to give me some suggestions. Okay, what do you see here? We're going to write this an as a formula. Tell me some part of this that we can do, that we can relate in terms of n. Perfect. 5 to the n. Say the last thing you just said. No, n will be fine. Because look, when we have n equals 1, we have 5 to the 1. Yeah. When we have n equals 2, we have 5 squared, 25. Yeah. N equals 3, 5 to the power 3. Yeah. Which is like 25 times 5, which is 125. Yeah. So n to the 5 to the n is doing exactly the thing we want on the bottom. Good. All right. What about the top? Minus 1 to the n plus 1. I agree that's going to give us the sign, because when n equals 1, we have a positive sign. N equals 2, we have a negative. N equals 3, positive. N equals 4, negative, and so on. So this thing will exactly give us the correct sign. Someone else tell me how we get the actual number on the top. N plus 2. Perfect. Yeah? And you see that this formula recreates all these numbers. Yeah? This is n equals 1, n equals 2, n equals 3, n equals 4, and so on. Good. So, not too bad, not too difficult. But sequences do not have to be defined by a formula, as I just said. So, example, we could let an be the nth decimal of the number e. So you'll remember e, it is just this number that has the property that when we take it to the power x and differentiate it, it still is equal to e to the x, right? So hopefully you'll remember that if you have a number b to the x and you differentiate it, then you're going to get log b to the x, yeah? Which you can just see in an elementary way. It's just a constant times b to the x, and that constant turns out to be log b. Well, e is just this particular number that has a convenient property that when we differentiate it, it's equal to itself, yeah? And that number is like 2.71 something, 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 yeah? 718281284 and so on and so on. It's like a number like pi, a so-called irrational number which has an infinite decimal expansion. Yeah? And we can define an to be the nth decimal point of this. So then a1 would be 2, a2 would be, oops, not 2, a1 would be 7, a2 would be equal to 1, a3 is equal to 8, and so on and so on and so on. Yeah? And that too is a completely well-defined sequence. Okay. We are going to visualize sequences in the following way. So, visual, I don't know how to spell it, visual, something like this. And this is how we do it. We're going to draw our x-axis and our y-axis. And then here at 1, here we have 2, here we have 3, here we have 4, and so on. Yeah. So on and so on and so on. And for each integer, we have that an is some particular number. So we're going to just plot that number on the y-axis. So if a1 was whatever 1, then we'd put a dot here. If a2 was, say, -2, we'd put a dot here. If a3 was 2, we'd put a dot here. If a4 was 0, we'd put a dot here. If a5 was 0.5, we'd put a dot here. If a6 was -3, it goes off, whatever. If a6 was -1, we put a dot here. If a7 was 3 again, put a dot here, right? So we have this infinite collection of dots that represents our sequence. And that's the way we're going to visualize it. That's the way we're going to think about it. Yeah? Cool. All right. So erase the board, do some more examples. An, which is equal to n over n plus 1. Let's try and visualize it. So when we have 1, then we have 1 over 2, which is here. When we have 2, we're going to have 2 over 3, which is a bit higher. Yeah? When we have 3, we have 3 over 4, and so on. When we have 4, we have 4 over 5. 5, we have 5 over 6, and so on. If we put 1 here, we notice that this thing is always less than 1. Yeah? This thing is always less than 1. However, as we keep increasing n, then this guy, this an, is getting closer and closer to 1, right? Because, for example, if we had n is 100, then we have 100 over 101, yeah? Which is a number pretty close to 1. Yeah? Still less than 1, but pretty close to 1. If we have 1,000, we have 1,000 over 1,001, still closer to 1. Yeah? For a million, we have 1,000,000 over 1,000,001. Yeah? Okay. So, if we think about that, then what that means is that if we take any line here underneath 1, then eventually our sequence will be above this line. Every single point going forward, right? Yeah, for any line we take underneath 1. So if your line was at 0.99, yeah, then eventually you will have that all of these guys will be above 0.99, right? And it could be even calculated. If we took just n equals 100, then 100 over 101 is bigger than 0.99. Yeah? And that's true going forward. So all the points are above this line. Yeah? But if we took a number even closer to 1, if we took 0.99999, yeah, it's still the case that ultimately all of these guys, all of these points of the sequences will be above that line. Yeah? So this sequence has a very particular behavior. As we're going towards infinity, the sequence is getting closer and closer to a particular value. And that value is 1. Yeah? And we can say that in a very precise way. What we mean by that is that no matter how close we put this line underneath 1, we're ultimately going to be above it. Yeah? Yeah? And that should seem very familiar to you. That is the concept of a limit. Right? So we say a sequence an has limit L if and only if the following is true. So I'm going to draw this in pictures rather than express it in the language of math, because it is well, firstly, the pictures are the main meaning, and secondly, it is easier for you at this stage of your learning to not see too many things written in math and to see pictures instead. So if we take our number L like this, okay, and we draw a horizontal line that represents L, then we say that n has the limit L if no matter what thickness around this number L we take, so let's draw a little kind of thickness around it. We can ultimately guarantee that all of the points in our sequence live inside this thin strip around the number L, so long as n is large enough. So let's put some points here. So this could be A1, this could be A2, this can be A3, this can be A4. It can do all kinds of crazy stuff for the first 100 million, 100 billion, trillion, zillion terms, whatever. But ultimately, at some particular number, 100 billion, trillion, zillion, something, something, whatever, all of the guys of our sequence is trapped inside this thin strip. Yeah? And if that's true, for every single choice of thin strip, then we say that AN has the limit L. Okay? So we write, if and only if AN is as close, I'm going to use the language of words now instead of math, is as close as we like to L for all large enough n. All and if you turn those words into a picture, it's exactly this picture. So as close as we like means that we can take any thin strip around this of any thinness at all. Yeah? That's the meaning of the words as close as we like. Yeah? And we can be as close as we like to L for all large enough L for all large enough N means that there is some number along the natural numbers, whatever that number is, such that for everything bigger than that number, we're inside that thinness. Yeah? Yeah? So the picture that represents this thing is exactly this thing. Okay, so you all learned about limits already in Calc 1. This, in a way, is a easier thing to understand because these are simpler objects than functions. And if the concept of a limit didn't feel completely comfortable to you then, you see it again now, and hopefully it'll click in more. So this is a metaphor that I like to use to explain the concept of limit. Imagine you are all working in some engineering firm, right? Probably that's your future. And you have a task of writing an algorithm that's going to calculate something. For example, what is the total amount of weight that a bridge can have before collapse? And to do this, you're tasked with finding the answer with a certain accuracy, but your boss is unclear about what accuracy is the customer wants. He says, I want you to write a program that will give me accuracy within 3%, but it might be that the customer wants it within 1%. So I want you to be able to do both things. And being a smart person that you are, you realize that you can do this by creating an algorithm that the longer you run it, the more calculated, the more accurate an answer it will give. So you say to your boss, okay, I can do that, but then I'm going to have computer time depending on the accuracy that is required. So if you tell me 1%, I'm going to need a lot more time than 3%. And your boss goes, okay, that's good. Computer time is not an issue. Just make sure you can give me the accuracy that the customer wants. So you write your computer program, you go to your boss, and your boss goes, okay, yeah, the customer said 3%, but now he actually wants 1%. So you go and look at your program, you go, okay, 1%, that's going to take 10 hours of supercomputer time. It costs you whatever this amount of money. Your boss goes, good, we'll do that. So you run the program, and you get your answer, and you go back to your boss, and he goes, yeah, thank you, that's great, but now the customer's changed his mind, her mind, and wants accuracy within 0.5%. So you go, okay, but then that requires more time. I can give you that if you allow me more supercomputer time. And the boss goes, yeah, do it. So you run it even further. You run your computer for another 10 hours, you get the answer within 0.5. And you go back to your boss, and the boss goes, oh, I'm so sorry, this customer is a pain. He's changed his mind again. Now wants the answer within 0.2. And you say, okay, this is the deal. I can get you within whatever accuracy you want, so long as you give me all the time that I want. If you give me all the computer time I want, I get you within whatever accuracy. So the customer can change his mind as many times as he wants. You can have whatever percentage error he wants, so long as I have all the computer time that I need to run my program enough times. And your boss goes, yes, that's fine. That's the deal. What you've just done is that you've made an agreement. You've made a contract with your boss that you can guarantee the accuracy within anything that he asks you, so long as you have enough computer time. Maybe it's going to take you 100 hours to get you within 0.5 accuracy or 0.2 accuracy. But that's fine because that's the deal that you've made. When you say something has a limit, you are signing a contract. You are making a deal. You're saying, I can get you to within whatever accuracy you want of this number L, so long as you allow me to take my points of my sequence far enough to the right above every number bigger than whatever number I tell you I need. Yeah? That is what a limit is saying. It's a very strong contract you've made. You've guaranteed to get within whatever error anybody can ask you for, but you have the right to take your sequence as far enough to the right as you need for that to be true. Yeah? So it's not a trivial thing. It's quite a promise you've made to be able to do this. Yeah? But this is what the concept of limit means. It's a strong thing to say. Yeah? Okay. Let us try and figure out some examples. This is example 4. Find the limit as n goes to infinity of n over n plus 1 if it exists. Well, this is an example we started with. We believe this thing does have a limit, right? And the limit looks like it's going to be 1. Yeah? And this is not too hard to show, right? So, solution. If we look at this n over n plus 1. Let's factor n from top and bottom. So we got n over n 1 plus 1 over n. N's cancel, we have 1 over 1 plus 1 over n like this. Yeah? And for sure, we can make this thing on the bottom be as close to 1 as we like, because we can make 1 over n be as close as close to 0 as we like. Yeah? Yeah? So that we can guarantee that this thing is as close to 1 as we like, because the difference between this thing and 1 can be made arbitrarily small by making this 1 over n incredibly small. I mean, if we want to write this in the language of math, what does it mean to be close to 1? It means that the absolute value of 1 minus 1 over 1 plus 1 over n is small. But then we can write this as 1 plus 1 over n over 1 plus 1 over n minus 1 over 1 plus 1 over n, like this. Yeah, and then the denominators are the same. We're going to cancel the 1. This is the same as 1 over n over 1 plus 1 over n. Yeah? And this number here, since the thing is on the bottom is bigger than 1, this thing is less than just 1 over n. Yeah? So you can guarantee that you are as close as you like to 1 by just taking n large enough. So if you want it to be within 1 over 100 of 1, then you just take n to be bigger or equal to 100. That's what this thing says. Yeah? So you're absolutely sure you can guarantee that this thing, which is this thing, is as close to 1 as you like. Do you see what I mean, people? Yeah? Cool. So you are certain this is true. So limit as n goes to infinity of n over n plus 1 is equal to 1. All right, let's do another example. What about this? What about the limit as n goes to infinity of minus 1 to the n? What would this be? Draw a picture to visualize this sequence, and then try and answer my question from the picture. What do you think this limit will be? Okay, so if it was 0, that would mean we could guarantee that it's arbitrarily close to 0 so long as we are far enough along towards the right. Can we guarantee that? So if this is 1 and this is minus 1, let's just draw it, right? So when n is equal to 1, we are at minus 1 here. When n is equal to 2, we are at 1 here. When n equals 3, we're at minus 1. When n equals 4, we're here. When n equals 5, we're here, right? Yeah? And no matter what possible choice you might have for a limit, we might try 1. It's not the case that we can guarantee that all the elements of this sequence are within some thin strip around 1 for all large enough n. That's just not true, right? Yeah? Because no matter what n we take, we have plenty of n, a whole infinity of n that are nowhere near 1, right? We'll go around -1, that's also true. Yeah? So we can't guarantee that an is close to any particular value. Yeah? If we could, we'd be able to trap everything within some thin strip, and that's clearly not the case. Yeah? So the guy who said 0, I see what you mean. You know, 0 seems like something which, if you don't have something, it feels like it should be 0. But if you say 0, it actually means we're close to 0, and that's not the case either. Yeah? Yeah? So in this case, the limit simply doesn't exist. Yeah? This limit doesn't exist. Yeah? So this limit does not exist. Okay. Let's try and squeeze in another example. No, not yet. Okay, I'm going to erase the board and we're going to do a few more definitions. So while I erase the board, I'm going to ask you to think about the following thing. We're going to try and have some clear, precise meaning of the statement that the limit as n goes to infinity of an equals infinity. So just like when you learned about limits for functions, when the limit is infinity, we don't say the limit exists, because when we say the limit exists, we mean as a number. However, there is a meaning to this. This will have a meaning. We can precisely define this. Yeah? Just in the same way we precisely were able to define the limit as x goes to a, f of x equals infinity. That's a vertical asymptote. Yeah, you've learned about that. You should be comfortable with that. Yeah. But think about how we would precisely express this. Think about how we'd precisely express this, and then we will give, does this mean? What can we mean by this? The limit as n goes to infinity, an. And think about how we defined the limit of the sequence being L. What would we mean by this? Think about the pitches. What would this mean in terms of pitches? This is 1, this is 2, this is 3, this is 4, this is 5, so on. What does it mean? What can this mean? How could we express the fact? How can you explain to your 4-year-old, 3-year-old nephew what infinity is? Suppose your 4-year-old nephew was going, is infinity like anything bigger than 400 is infinity? You'd say no, right? Yeah? So how would you try and explain to your nephew what infinity was? You'd say it's bigger than 300, it's bigger than 400, it's bigger than any number you can give me, right? So the way we're going to make sense of this is we're going to say that no matter what big number we like, so we take any big number, this, so I wish I had more space here. Let's say this number was your favorite big number. 10, 100, 1,000, million, trillion. Yeah? Let's draw a line here. Then this thing goes to infinity so long as all the points of this sequence are above this line for all n far enough to the right, bigger than some number that you choose. Yeah? So if for any horizontal line, no matter how high it is, you can guarantee that all the points of your sequence are above that horizontal line for all large enough n, for all n far enough to the right, and when you have the right to choose where it starts to be above this thing, then that thing is going to infinity. So in the metaphor of the contract, your boss says, I want you to guarantee the sequence to be above 10, 100 trillion zillion. And you say, okay, I can do it so long as you let me choose all n bigger than 400 billion trillion zillion killion, whatever. Yeah? If you can do that, no matter how big the L is, then that's the same as saying this thing goes to infinity. Yeah? Because what is going to infinity? It means ultimately being bigger than any big number that you can choose. You see what I mean? Does that make sense? Give me a thumbs up if that's making sense. Okay, cool. All right. So, means that a n is bigger than L for all large enough i.e. we can find some large number n, and n will depend on L such that a n is bigger than L for all n bigger than capital N. So this, in words, for all n large enough, if we express this more precisely in the language of math, that means that we can find some capital N such that a n, little n, is bigger than L for all little n bigger than capital N. That thing here for all large enough n, actually let's write the entire thing. This thing here, in the language of maths, is more precisely expressed like this. And if you are trying to explain this to a computer, this is what you would write, right? For those of you with a bit of programming experiences, this will make more sense. And it's such a big advantage to be doing some programming when you're learning math. All right, cool. That's what it means for the limit to be infinity. Yeah? Yeah? Cool. All right, let's look at this example. Damn it. Example 5. The limit as n goes to infinity of n over the square root of n plus 1. What is this? Try and visualize this. Think about this as a collection of points on the real numbers. Oh, sorry, above the real numbers. What's this limit? What's this limit? If you're really stuck, just put in numbers, large numbers into this expression. Come on, give me some suggestions. No? Infinity. Why do you say infinity? Yeah, so for very large n, right, or actually for any n bigger than 1, the square root is smaller than the function itself, right? Square root of 4 is 2, square root of 9 is 3, yeah? Yeah? So if we take n getting bigger and bigger and bigger, the thing on the top is a lot bigger than the thing on the bottom. In fact, it keeps growing faster than this thing. So here's another very useful way to think about sequences. If we have a function, so if we have function f from the real numbers to the real numbers, where f on the integer n is equal to an. Let's visualize what that means. So here is A1, this is A2, this is A3, this is A4, this is A5, A6, A7. So that means that these guys live above the numbers whatever. This lives above 1, this lives above 2, 3, 4, 5, and so on. And the meaning of this thing is that we have a function where on these particular values it agrees with this, which on this picture means that the graph goes through these points. Yeah? That's what it means. Yeah, we'll see that. Yeah. Then the limit, or actually, if the limit as x goes to infinity, f of x equals L, right? Horizontal asymptote. Well, in the case when L is finite, this implies that the limit as n goes to infinity, an is equal to L. Yeah? Because you've all learned about horizontal asymptotes, that means exactly that. We can guarantee the function is arbitrarily inside a thin strip around L so long as we are far enough to the right. Yeah? That's the meaning of horizontal asymptote. Yeah? That's the meaning of this thing. And if all the points of our sequence live inside the graph, then it's obviously also true that all the points of our sequence is inside this thin strip around L2. Just the pictures, right? The pictures make that completely clear. Yeah? Give me a thumbs up if you know what I mean. Cool. All right. And what's also true is that L can be infinity. So if the function goes off to infinity, then the sequence which lives on the graph also has to go off to infinity. Yeah, for exactly the same reasons. So, if we look at this guy, we can have this function f of x, which is equal to x over the square root of x plus 1. Now, I asked you what happens when the limit of this thing goes to infinity. Hopefully, you would all very quickly tell me this thing goes to infinity, because morally, for very large x, this square root of x plus 1, is a lot like just square root of x. Because for very large x, this plus 1 makes very little difference. Yeah? Increasingly little difference as x gets bigger and bigger. Yeah? So just from all your knowledge from Calc 1, you should be happy with this thing is equal to infinity. Yeah? And therefore, the limit as n goes to infinity of our particular sequence, n over the square root of n plus 1, is equal to infinity. Because this is also true when n equals infinity. And again, when n equals infinity, we don't say that the limit exists. Even though we write this, we write down what the limit is, we don't say the limit exists, because when we say the limit exists, we mean as a number. Okay? So don't get this thing twisted. We write this is a true fact, we apply it, but this doesn't mean the limit exists. Whenever you hear the words the limit exists, it's just a shortcut for saying the limit exists as a number. Okay, I forgot my watch, so tell me how much time I have left. Okay, 6 minutes. Good. All right, so looking at this guy, either because you think about this living on the graph of this function, whose limit as x goes to infinity is infinity, or you just visualize it. You just see what's happening as n gets bigger and bigger and bigger. Yeah? Or, okay, maybe that wasn't helpful. So just look at this. So n is like square root of n, square root of n. Yeah? So this thing over here, n over square root of n is like square root of n, which is blowing up, and n over square root of n plus 1 is almost the same thing as this thing, because for very large n, we don't notice this plus 1 over here. Yeah? So for large n. So if you can do horizontal asymptotes for a function, you can also figure out limits. In fact, it's easier. Sorry, let me say that whole thing again. If you can do horizontal asymptotes for a function, then you can also figure out limits for sequences, because it's actually easier. These are easier, more simple things to understand, sequences, than functions. Functions are more sophisticated mathematical object. A function is like, okay. If you don't understand what I'm about to say, just forget about it. But a function is like a sequence defined for every x over some interval. Yeah? So a function is something more sophisticated, more complicated than a sequence. A sequence is just defined on the integers. Yeah? So you're very comfortable with functions, but sequences are actually an easier thing. Okay, I want to maybe just tell you a couple more things, or maybe one more thing. All right, I want to do one more example. Those of you who have to leave at any time. Example 6. What about this? The limit as n goes to infinity of the sequence log n over n. What will this be? If this limit exists at all. What will this be? Yeah, we could do, okay, tell me when we can use L'Hopital. When we have a function in indeterminate form, right? Yeah. But we're not talking about functions right here, we're talking about sequences. So how could we go forward? Well, what's the basic thing I want you to do? I want you to visualize this raw picture, yeah? So if I start to plot these things, what would it start to look like? Let's start with 2. So log 2 is whatever, some number over 2, yeah? And I'm going to have log 3 over 3, and log 4 over 4, log 5 over 5, and so on. If I did that, how would I be plotting these things? Where would these dots be going as I start to plot it? What have you used? Keep going. Perfect. This is the graph of log, and this is the slowest growing elementary function. Log grows incredibly slowly. Log is unwrapping e to the x, and e to the x grows incredibly fast, right? So log is slower than x, it's slower than square root of x, it's slower than x to the power 1 over 4, it's slower than x to the 1 over 100 million. It is the slowest growing thing around in elementary functions, right? And it's certainly slower than just x itself. So if we consider the competition between who grows faster, log and x, y equals x, let's write it this way, that's a complete mismatch, right? Log is so much more slowly growing than x that when we consider the ratio of the two, it's going to go to 0. Yeah? That's how I want you to know the answer before applying any rules, before applying any technology. I want you to be familiar, as I've said many times, I want you to be very familiar with these elementary functions, to know their behavior, and then be able to quickly get an answer for stuff like this just from that knowledge, which you can. Yeah. So with very high probability, you should feel this has to tend to 0 because I know what log is like, and it's going to get killed when we compare it to just y equals x. Yeah. Yeah. So if I was asking you this question, so consider this question from Calc 1. If I wrote this, hopefully before you applied L'Hopital's rule, you'd go, okay, but I know the answer because I know about the rates of growth of log and the rate of growth of y equals x. Yeah. Yeah. But if you do want to apply L'Hopital's rule, you can, because as you've told me, it's in indeterminate form. It's infinity over infinity, so we can just differentiate top and bottom. So by LHOP, we're going to have that this is the same as the limit as x goes to infinity of 1 over x over 1, which is just the limit as x goes to infinity of 1 over x, which of course is 0. So we confirm what we know with this rule. Yeah? Okay, but that's about functions. Now relate this to this. Relate this to our sequence. Indeed, but implicit in that is this observation that I told you just on the last board, that this function f of x, which is log of x over x, has this property that f of n is equal to our sequence, right? It's equal to these guys. So by this theorem, the limit as n goes to infinity of the sequence is the same as the limit of the function as x goes to infinity. Yeah? Yeah? Do you see what I mean? Cool. So this is our function log x over x. Yeah? And by our tools from L'Hopital's rule, we can confirm it goes down to 0. And that allows us to conclude that the sequence goes down to 0. And that is how we can definitely answer this question. So if you were doing a free response, I would want you to firstly say that you know the answer is 0 because you know that log grows much, much more slowly than y equals x. And then do this kind of stuff to confirm it with some theorems, some principles that you've learned. But on a multiple choice, hopefully this would take you like a millionth of a second to come up with the answer, because you know so well how slowly log grows compared to the function y equals x. Okay, cool. All right, so we'll talk more about sequences on Monday. Hopefully this starts to make sense. Watch the video over. If this doesn't feel clear to you, make note of anything that doesn't seem clear, and you can talk with me about it on office hour. Otherwise, have a good weekend, and I'll see you all on Monday. Bye-bye.